My name is Brad, and today I'm going to be walking you through a simple design example and show you how you can use the new Shearline module available in Mass that can be used to help you out with your design. Now, if you've taken our most recent Engineered Masonry Design course offered by the Canada Masonry Design Centre, you might recognize this problem from one of the take-home assignments that was part of the course. And what we're looking at here is just a basic shear wall system that has openings and movement joints arranged in such a way as to illustrate the way that we distribute loads in Mass. Now, this is the same method that is described in Dr. Drysdale and Dr. Hamid's textbook, Masonry Structures, Behavior, and Design. We'll start by showing you how you can model this in the new Shearline module available in Mass version 2.0. Start by just launching the program and selecting New Shearline, and this is what you'll see. It should look pretty familiar to you if you've used Mass before and designed a shear wall, but just to get you started, I'm just going to put in my outer dimensions. So I have a height of 7 meters, and I have a length of 18 meters. And as soon as I enter these in, you'll see that it gets drawn on here with those same dimensions. At this point, I can start adding openings and movement joints. You can see I have a tab for each up here in the input section. So I'm going to start by placing my movement joints, and I can do this in two ways. So when I have the movement joint tab selected, I can click to place movement joints on the shear line. I'm just sort of guessing right now. Another way you can do it, though, is by clicking the Add Movement Joint button and entering an exact location. So this third movement joint, I'm going to put it at 16.8 meters, and as soon as I hit enter, it will place it on here right away. And then I can actually edit the locations of the existing ones. So if I wanted to change this to 8.8 meters, then if I just hit enter, it moves it over, of course. Now I actually want this at 9 meters, and so I'm going to move it back. You'll also notice that when you enter things in using the drawing window, it snaps everything to the nearest head joint, where when you enter things in here, it actually takes exact dimensions. So if you wanted to have cut units in your shear walls, then you could put it actually at any location you like and do it that way. I can do the same thing with openings. So I'm going to start by selecting the Openings tab, and I can just click and drag here, and I just go corner to corner. As soon as I let go of my mouse, it places the opening. I can edit it in any direction I like and move them around as well. And like I said before with the movement joints, when you're using the drawing window, everything gets snapped to the nearest head joint. So same thing with this opening. I place that there. I'm going to put another man door over here, and then a great big bay door as well. And then if I want to change any of these dimensions, I can choose where they are. So for this opening here, for example, if I want to change the height, I can change this to 800. And if you watch this opening here, as soon as I click enter, it'll be changed and brought down, and I can use the opening. I can change that height there too. Now that I have my overall geometry set up, I can start to model how my shear wall is going to behave. And before we do that, let's just take a quick step back and look at exactly how we distribute these loads. So as I mentioned earlier, Mass uses the same technique that's outlined in the textbook. We determine how much load goes to each element by distributing it according to relative rigidity of each wall panel. Now, it's a very simplified approach. It's based on fundamental structural analysis, and we assume elastic behavior. And I'm going to illustrate it using this example. You can see here that we're looking at a shear wall that's separated into 4 segments by our movement joints. Now, each wall panel is going to take a portion of our lateral load. This load's directly proportional to the rigidity of each panel. So if there's one panel that contains the bulk of the total rigidity, we also know that it's going to take most of the applied load, such as wind or seismic. So how do we determine the rigidity of each panel? When we have multiple panels that are linked together in parallel, such that they share the lateral loads, they act and they deflect together. The deflection of each panel is going to be exactly the same, and the total rigidity of the system is simply the sum of the individual wall segments. Now, this is notably different from the case where we're looking at piers that are stacked vertically on one another in series. The total deflection in this case is going to be equal to the sum of the deflection of each of the individual elements. Rigidity is equal to the inverse of deflection, also expressed as the stiffness per unit load. Now, by applying simple beam theory for elastic sections, we can approximate this for a rectangular cross-section, which we use to represent our masonry walls. There are 2 components of this total stiffness. We have the flexural and the shear component of that. So this process is simplified By limiting the loading and boundary conditions assumed by our walls, we can only look at the top as being fixed or as being fully cantilevered. Now, getting the deflection is as simple as using the right formula, depending on which boundary condition you assume, whether you use the equations on the left for cantilever or the ones on the right for fixed wall rotation. You'll also see the equations as they appear en masse. The ones at the top there, they appear a little bit more pixelated on here. That's because they've been enlarged. If you've done these sorts of calculations by hand, you may be familiar with using the second row of formulas you see there. It's the exact same formula. It's just been simplified for a rectangular section, and the shear modulus G is assumed to be 40% of Young's modulus of elasticity. That's how we got to those equations. So how do you decide whether the top of a pier is fixed or not? This is the million-dollar question, and if there were consensus guidelines, then Mass would be able to take care of this for you. Unfortunately, there are no clear-cut guidelines for what counts as fixed and what counts as being cantilever. So it actually ends up to being up to the discretion of the designer to model this behavior as he or she sees fit. Now, if we look at our example shear line, you can see the highlighted pier on the left has no masonry above it, and so it's free to rotate freely without any sort of restriction from the top of it rotating. Now, if we look at this area on the right, this pier that has a significant area of masonry above it, it would tend to deflect more as a fixed pier because it has all this masonry that is connected, preventing it from rotating. Now, while I'm talking about these equations, I should make a special note to point out that all of these deflections and rigidities are based on elastic, uncracked section analysis. If we're designing with reinforced masonry, we're obviously designing for our wall to crack, but then also we have bars yielding and more ductile behavior in our shear walls. So the important thing to remember is that we're not concerned as much with the rigidity itself as much as we're looking at the relative rigidity and comparing the rigidity from one area of masonry to another. So if we're looking at similar reinforcement configurations, in many instances, we're going to have the same relative stiffness, whether or not we're looking at elastic analysis or inelastic analysis. It's just the relative difference that we're more concerned with, and so that's why this analysis is generally okay when we're distributing in-plane loads around openings and movement joints. Now, in order for us to distribute our loads, we need to know the total rigidity as well as the rigidity of each of these individual panels. So let's start with the easy ones. Let's look at the two at each end. Now, first of all, they share the exact same dimensions, and they have the same wall properties, so we know that the rigidity of panel 1 and the deflection of panel 1 is going to be equal to that of panel 4. Now also, we know that these panels are cantilevered, having no masonry above them, preventing the rotation, and so we know that we can use the cantilevered expression. Now if we keep everything in terms of EM, T, and V, we get a deflection value of 811.48, and since the rigidity is the inverse of deflection, we get a rigidity of 0.0012. Now remember, this number is meaningless by itself, but it'll come into play once we compare it to the rest of the wall panels. Now moving on to panel 2, you can see it's a little bit more complicated as we now have two openings within this wall panel. Now if you recall from earlier, we can get the deflection of a wall by adding up the deflections of each of the vertically stacked components. Now openings can be taken into account doing something similar, where what we do is remove a strip from the solid wall and replace it with the masonry on the other side. So we do this with reflections. We start with the solid wall, and then we subtract the deflection of the strip that encompasses the opening, and then we add in the deflection of the two components on either side working together. It's very important to remember that when it comes to adding the deflection of the two piers working together, you can't simply add in the two individual deflections together. Now if you remember from earlier, when you have multiple panels that are deflecting together, you have to add their rigidities to get the total rigidity. So we do the same thing here, where we need to find the total rigidity of these piers, and we just add up the two individual rigidities together using these two formulas. These rigidity values can be easily calculated using the dimensions of the piers, and when you sub it back into the main deflection equation, you get something that looks like this, where instead of just having the deflection of the piers together, we have the inverse of the sum of the inverse of these two deflections. So now that you have all the background information, let's actually calculate the deflection of panel 2. So we start, to get the deflection of the whole thing, we need to look at the solid area, ignoring both of the openings, and then we subtract from that deflection the deflection of just the strip that encompasses the openings, And then we need to add in the deflections of the piers working together. So remember, for that deflection, the rigidity of these piers working together is equal to the sum of those two rigidities. And so we can find those out. First of all, we have straightforward rectangular areas. So we have the deflection of the solid area, ignoring the openings. So you can see I used the cantilever equation. That's because this isn't fixed to the top. Whereas when we're looking at the strip and the pier on the left here, there is significant area up here. So as it's deflecting, its behavior would more represent a pier that is restricted from rotating at the top. So when I sub these into my expression, I still have an unknown here. We need to look at the deflection of this pier and take the second opening into account. So when I look at this, it's the exact same process. We just do it again. So to get the deflection of that pier with the opening, we start by taking the deflection of the solid pier. We subtract from that the deflection of the strip that encompasses the opening. And then we need to add in the deflection of those two piers named A and B. And to get that, we take the inverse of the rigidity and we add those two rigidities together to get the total rigidity. And so now we're looking at straightforward rectangular sections in all of them. And so when we sub in our values here, I'm just subbing in numbers. It's all using the fixed end condition. And we can actually get this 2.16 value you see here when I sub everything in. That is the deflection of this area here, looking at the opening being taken into account. So now that I have that number, I can go back to what I had before, where this value was unknown. I can sub in the 2.16. And so now, when I put that in there, I get a deflection value for panel 2 equal to 6.63. And of course, if I look at the rigidity as the inverse, I can just do 1 divided by 6.63 to get that 0.151. Now remember, once again, this number by itself, not important. Same with that delta value. That's not a drift value. We're just looking at these relative deflection values to try and see where our loads are going. Now going back to our full wall, we now have the rigidity of 3 out of the 4 panels. So in order to get that R total value, we need to find the rigidity of wall panel 3. So then, sort of jumping through here for the sake of time, we're going to take 2 strips. We're going to start with the large opening, then do the smaller one, exactly the same as we did for our panel 2. And jumping to the final answer here, we would have a deflection value of 17.83 and a rigidity being the inverse of 0.056. So now that we have this, we can go back to our shear line. And now these rigidity values get a little bit more important because we have an idea of what our total rigidity is. So adding up the 4 rigidities, since they deflect together, we have 0.209. And this is important because once we put these all together, we can look at the ratio of the rigidity of each panel to the total, and that gives us an idea of the percentage that each panel resists. So you can see these 2 end panels barely take any, and this wall panel here, this is by far the most rigid. That's because compared to this panel, we see a lot of this panel is we subtracted the deflection of this strip and added in these piers, which had very high deflections. It's all about the aspect ratio. So as soon as you have, we have these taller, less stocky, obviously less squat piers, that reduces our rigidity a lot. So in our original example, there was an applied load of 255 kilonewtons. So using these relative rigidities, we can look at panel 2 if we want to know how much of that 255 goes to panel 2. It's just equal to this percentage, and so 184.1 kilonewtons is what's resisted by that panel. So what about the loading within a wall panel? Now we've already calculated the rigidities of each of these elements when we were determining the rigidity of the whole thing. So fortunately, all of the work's done for us. So looking at panel 2, we know that whatever load applied at the top is going to be shared between these 3 piers. Now it would be tempting to simply take the rigidities of pier 1, pier 2, and pier 3, add them together, and look at the ratios, but you would definitely be wrong if you do that, so do not do that. A lot of people do that. Please do not mess that up. Now before we look at piers 2 and pier 3, think about how the wall is actually deflecting. What's happening here, we're splitting the load between this pier 1 and the combination of areas 2, 3, and 4 that we have here, taking these openings into account. Now it's not really too difficult because we've already actually done the work. We know the rigidity of this area, and so we can find the total rigidity by simply adding those 2 together. And then before we look at piers 2 and pier 3, we can look at these ratios and know that 11% of whatever load is applied at the top of our shear line, 11% of that load goes to pier 1, and then the remaining 89% goes to piers 2, 3, 4 as a combination. So now that we know how much load is going to the right of this opening, we can do a second load distribution. So of this 89%, how much of that goes to Pier 2 and how much of that goes to 3. So we do the same thing. We already know the two rigidities of Pier 2 and Pier 3. So by doing the same thing with the ratios, we actually have a 60-40 split, where we have 60% of that load goes over here, and then the remaining 40% is to Pier 2. So now if we go back to our entire shear line doing the exact same thing for panel 3, we have an idea of exactly where all of our loads are going. And this is how basically we do our in-plane load distribution. The MASS version 2 Shearline module does all of this in just a matter of seconds. You can see here if I click on the load distribution tab, all of my percentages show up here, exactly the same as what we just calculated by hand. And if you want to see where these areas are, if I click on the panel properties tab up here, this lists all the different areas. So for example, Pier 2-1, it takes 8% of the total load that's applied at the top of the shear line here. Pier 2-1, if I click here, it shows up right there. And I can scroll through and I can click on any of these other areas and it shows me on the drawing where these are in my shear line. Now we were talking about the fixities before. You need to go through each of these areas and choose whether or not they behave as a cantilever or fixed. By default, these will all be cantilever when you first start. But then what you'll need to do when you go through all these piers is to click through and say, oh, do I think this one will behave as a cantilever or as a fixed? That's one thing that since there's no consensus on it, you just have to look through and check them out for yourself. Now once you have your fixity set up here, you'll see we have this design box. What that does is when I click on it, it creates a shear wall tab down here that has the same dimensions, but it's linked to the Shearline module. You'll see how that works in a bit. So what I want to do is click on all the different piers in here that might be the critical section for my wall. So as I click through here, you can see that only the solid rectangular areas can be selected. Parent piers, so the areas that have openings within them, or strips can't be selected and opened as their own shear line. So I'm just going to click through here. I'm going to see where my critical section might be. This one here, I'm not too sure. Realistically, what will probably end up happening is I'll get a design where I'll have some bars in this pier and some bars in this pier, and I would just extend them up for my actual design. And then I'll go down here, select Pier 4-1. So now actually if I hold Control, I can select multiple piers. So just to sort of visually show you which areas I have selected here. So you can see I've pretty much got all the possible critical sections. I could also select this area as well. I'll select that. So once I've got these selected, I can now click on the moment deflection design. It actually will also design for shear. This is the very long design loop, and what it's doing right now is designing all of these shear wall modules for both moment and shear, and it designs it multiple times. You'll see on here it'll reference there being multiple loops that it goes through. What it's actually doing for all of these piers that we selected, it's distributing the loads to them, it's designing each one, coming up with the design, looking at the governing design, and then trying that same design for all of the other piers so that we get a uniform design at the end of the day looking at our shear line. So this can take some time. You can see I selected quite a few piers on here. The more piers you select here, the longer this process will take. Same thing with your file size. When you save this, now we're saving something like 12 shear wall modules, and so the file is larger. So now that I have my results, I'm just going to make this window a little bit bigger here. I can see what exactly is happening. So I'll jump down here and show you my final design. It's using a 20 centimeter, 25 MPa unit. Now this is the group design section. You see that they're all designed using the same block, the same uniform design. But if I look at my critical pier design, this shows what the minimum passing design is for each element. So if I look for that 20 centimeter, 20 MPa, 25 MPa block, Pier 2-4, if I go on here and select Pier 2-4 to see where it is, this seems to be the governing element because that block size and strength is being used in the rest of my design. Now if I go up here also, we show the results in a different way. You can see the moment results and shear results. We show you the factored moment, the moment resistance, same with the factored shear and shear resistance, but we also show you these handy ratios that show up on here. Same thing with for shear, and you can see the higher these ratios are, the closer these piers are to being at their capacity. So if I want to investigate any of these individual piers, I can do that in the MASS Shearline module. So for example, if we're looking at Pier 2-4, the pier that we decided was our critical pier, if I go to our load distribution, I can see that Pier 2-4 would have taken 38.4% of our original applied load that was applied to the top of the shear line. So if I actually click on Pier 2.4 here, it'll open it up as its own shear wall module. I can see it's placed joint reinforcement at every course. I've got 4 vertical bars, so it's partially grouted, half hollow. And when I click on my loads here, these are all the loads that are applied. And in particular, this earthquake load, this is the one we were distributing originally in this example, but you can see 97.9, that's equal to the 38.4% of the 255 that was originally applied. Now really quickly going back here, you can see all of the results that were available to you in Mass version 1. You see you've got all your load combination information, where your bars are, you've got all your shear information, and then if you click on the detailed button here, it'll also generate all of the equations that were used as well as the CSA references. So just to wrap things up, I want to thank you for taking the time to watch our video and learn more about the software. If you want more information, you can check out our website at masonryanalysis.structuralsystems.com, or if you want to contact us or give us some feedback, you can email us at mass@canadamasonrycenter.com. Once again, thank you for watching.